welcome to CEC lectures. Myself Dr. Preeti Jagani. I am from Department of Computer Science, Aryabhat College, University of Delhi. So as you all are aware that presently we are learning our series of advanced data structures and algorithms, and within that in the previous lectures we have completed our Bellman-Ford algorithm, which was an algorithm in order to find shortest path even in the presence of negative edge weights. And now we are going to begin today with our new topic, which is known as union find data structure, or we can call them as one of the disjoint set data structures. So when we talk about any particular data structure, the efficiency of any algorithm depends on using a data structure which is kind of we can say efficient. If we are using an efficient data structure, we can have an efficient algorithm, or we can have efficiency of algorithm to be increased. Or if our data structure is not so efficient, then it is definitely going to affect the time complexity, or we can say in totality the efficiency of the algorithm. So basically a good choice of data structure can reduce the execution time of an algorithm, and it is a very kind of important or crucial point when we are designing the algorithm, that what kind of data structures, which particular data structure you are using for a particular application. And union find is actually such a data structure that falls into the category that if used properly with the kind of designated applications, it is going to reduce the execution time of the algorithm. Now this union find data structure, if we go into deeper, we can see that it is used to maintain the knowledge of connected components of a graph and query for them quickly. Now what all queries can be kind of made, that depends on what kind of operations you are going to allow for that particular data structure. So here we can say a union find data structure is related to kind of maintaining a record of connected components of a graph, and then obviously we can query them, we can kind of retrieve the information for them. So union find, if we talk about it, represents a subset using a rooted tree where each node points to its parent instead of its children. So that is why we are calling it as rooted tree. So in computer science normally you have seen that our trees are actually inverted trees, but here the union find is going to represent a subset, or maybe a component set, and this will be represented using a rooted tree. Each node here is not pointing to its children, but inversely each node is pointing to its kind of, we can say, root. And if we really want to find out the subset in which a particular element lie, that is a kind of a simple operation here. Then in this situation we keep traversing up the parent pointers until we hit the root. So root here is going to represent, we can say, the whole tree. And if we say if we want to join the two subsets, or if we want to make a union of two subsets, that is also very easy. Here in order to union two subsets, we are going to assign the root of one of the two trees to point to the root of another tree. That all these operations we will be kind of taking with the help of examples as well. So in order to union two subset, we are going to assign the root of one tree to point to the root of another tree, and now all the elements of the two trees will have kind of same root, because only one root is allowed in case of trees, and hence they are belonging to same subset, we can say. But when we talk about the connected components of graph, one point which is very important and worth remembering is that your union find is not applicable on directed graphs. It is only applicable to the undirected graphs, and most of the problems that can be solved by this union find can also be solved by DFS connected components approach. So, please recall the data structures and the algorithm series which we have already done through the means of this particular channel. There was an algorithm which was depth first search, and the within the applications of depth first search we have also seen we have seen one connected components approach. So, many of the problems that can be solved by this union find can also be solved by DFS connected components approach, but yes, obviously the we can say complexity is going to be very different. As we talk about the complexity, we will be discussing about the amortized complexity or the amortized analysis of this union find problem as well in our upcoming lectures about this topic. So, union find, as I have told you, is also kind of a disjoint set data structure, or union find is a type of a disjoint set data structure. So, first of all, let us understand that what is this disjoint set data structure. So, when I am using the term disjoint set, that means it is actually a data structure which maintains a collection at, let us say, capital S, and this collection is having S1, S2 till Sk elements, and all these elements are disjoint dynamic set. So, each and every element here is a set, and all these sets are dynamic is one, because they keep on changing. We can include the elements them in these, or we can change the representative elements which are roots, and more specifically the important thing is they are disjoint, and each set, as I have told you, that each set can be identified by a representative which is some member of the set. So, any particular, you can take the first member or you can take any random member. So, there is going to be one particular representative that is going to be identification for the members of the set. So, let us say we have a set of n elements, and these elements are going to be partitioned into further subsets. Now, what are we going to do, or what is the task which is given to us with the help and that is to be achieved with the help of these union find data structures is, we need to keep track of connectivity. That is what I was telling you, that in order to maintain the connected components, or in order to query for the connected components of a graph, this data structure is going to be used. So, finally, or the goal is to keep the track of the connectivity of each element in the particular subset, or we can say the goal is to keep the track of the connectivity of subsets with each other. Both can be the task. Now, in order to do this operation efficiently, one can use the union find data structure. Now, why I am saying that in order to use this operation efficiently, just because that this kind of task can be achieved with the help of any other data structures also. As I have told you that most of the applications which find union find as the appropriate data structure can also be handled with the help of DFS connected components approach. But if you really want to do this kind of task efficiently, union find data structure should be kind of the choice. Now, let us try to understand this with the help of an example. So, let us say there are 5 people starting from A to B. So, A, B, C, D, E. Now, A is a friend of B, B is a friend of C, and D is a friend of E. So, here if you can see A, B and C, because A is a friend of B, B and B is a friend of C, these A, B, C are connected to each other. So, they are going to form one particular set, and then we have D and E, they are also connected to each other because D is a friend of E. So, here we will be having 2 subset among these 5 elements. So, first subset will be A, B, C, and the second subset is going to be D and E. So, now if we want to check that whether one friend is connected to another in a direct way or maybe in an indirect way. So, what is the direct way? So, A is a friend of B or vice versa, B is a friend of A is a direct way to get connected. And if I am saying A is a friend of B and B is a friend of C, then A and C are connected but in indirect manner. So, if we want to check the connectivity, or if we want to find out that whether one friend is connected to another, whether in a manner directed or indirected way, we can use union find data structure. And with the help of this, we can also determine that there are two disconnected subsets, as I have already told you. A is a friend of B, B is a friend of C. So, here two different subsets will be kept as A, B and C is going to be the one subset, and D is the friend of E. So, D and E is going to be the another subset. Now, how are we going to check that whether the elements are friend to each other directly or indirectly? For this, what are we going to do? We actually want to find out the representative of the particular set. So, for example, let us consider this set A, B, C. So, for this A, B, C, I am assuming A as the representative. So, when I am going to ask that to which set B belongs, the answer will be the A is the representative, A is representing the set. So, answer to this will be that B is belonging to the set whose representative is A. Similarly, if I am going to ask the same question to C, that to which particular set you are belonging, then the answer will be that the C belongs to the set for which the representative is A. And similarly for A belongs to the set for which it is the representative, or A itself is the representative. So, for all the elements of one particular set which are A, B and C, the representative is common, that is A. So, in this situation we can say that yes, these elements are connected, whether directly or indirectly. And why these are connected? Because they share the same representative. Similarly, if we talk about D and E, and I am assuming the representative of this set, the set can have only one representative. So, I am assuming that the representative of the set is, let us say, D, then the for the element D the representative is D, and for the element E the set representative is D. So, that means they are also connected. Now, when we talk about any data structure, the important thing along with the structure of that data data structure, the very important thing is what kind of operations we can perform on that. So, for example, let us take any data structure, let us take a stack. So, push and pop are the operations, let us take the queue. So, NQ and DQ are the operations. So, when we talk about this union find data structure, there are couple of operations, or there are few operations which are important, and these are, one is find A, another one is union A comma B, then third one is find A comma B, and the fourth one is make set X. So, basically these are not we can say non-overlapping operations, they are overlapping operations. So, when we talk about find A, this find A actually finds the component that A belongs to and return the root of that component, which is nothing but the representative of that particular subset. As I told you that in the set A, B, C, let us say the representative element is A. So, for B it is the set whose representative is A, for C it is also the set whose representative is A, and same goes with A as well. So, find within the bracket A is going to find the component that A belongs to and returns the root of that component. If I am going to say union A comma B, which is another operation, union A comma B, as the name suggests, it connects two elements A and B by making the root of A point to the root of B, or it could be vice versa by making the root of B point to the root of A and this is done by saying parent of root of A will be given the value of root of B. So, this is a simple operation. So, union A comma B is actually kind of we can say connecting the two different components and assigning one of the representative of this connected component. Now, that representative can be from this particular set or that representative can be from this particular set. That is you can say that you can decide or that a programmer can decide. So, we have seen two operations, one is find A, another one is union A comma B. In the line there comes the third one, which is find A comma B. So, find A comma B will finds if A and B belong to the same component. So, if A and B have the same root, or here we can say if A and B have the same representative, then we can say that find A comma B is going to return true. So, here we are going to find if find A is equals to find B, if the representative element or root of the set to which A is belonging is given by find A is equals to the root of the set to which B is belonging, then these find A comma B is going to give you kind of we can say a true value. Then the another operation which comes here next is make set X. So, make set X is going to create a new set whose only member, and obviously because of being the only member, representative also will become X, X will also become the representative, because just a new set has been created and the only member which is available within that new set is X, and hence because of being the only member, this is going to be kind of we can say the only because this is the only member, this is going to be representative as well. And please remember that since the sets are disjoint, we initially told you 2-3 times that the initially the sets are going to be disjoint. We require that X not already be in some other set. So, when we are making a set X, it is to be ensured that this X should not be already present in some other set, because we are talking about disjoint set data structure. Sets are disjoint here, and if your X is already present in some other sets, and then on top of it you are creating a new set with the only member X, then this is going to give you a clash. That means now the sets are not disjoint, but here we are looking for only disjoint sets, that is the condition. So, when we say union X comma Y, so this union X comma Y or union A comma B, that unites the dynamic sets that contain X and Y. Let us say these sets are denoted by S of X and S of Y. These two sets are united into a new set, that is going to be the union of these two sets, and we assume that these two sets are disjoint prior to the operation. The representative of the resulting set will be any member of S of X, will be any member of S of Y, or will be any of the representative of the earlier representative, which is either the representative of S of X or the representative of S of Y. Any element could be the new representative or new root of the set. So, although we can have many implementation of this union operation, which is specifically choose the representative of either S of X or S of Y as the new representative. So, that is what I told you, either you can pick a random element from the union of these two elements, or you can choose already designated representative of either S of X or S of Y as the new representative. Now, one thing which is very important, very important with this union thing is we require the sets in the collection to be disjoint, and this is a condition which we have uttered many times. So, in order to make these collections, in order to make these sets in the collection to stand disjoint, conceptually we need to destroy the two sets S of x and S of y, removing them from the collection S. So, when we are putting the union of S of x and S of y into our collection, ideally or mandatorily, S of x and S of y, these two individual sets are to be removed just because of the condition that all the sets in the collection are needed to be disjoint. Or we can say in practice, one can absorb the elements of one set into the another set. Now, if we look into this find set X or find set A or find A, whatever, I mean what any thing could be a appropriate terminology. Either you say it find A, that we have seen earlier, or you can say find set X, that returns a pointer to the representative of the unique set containing X, and determining or specifying this as the unique, that that is to ensure that the sets are disjoint. So, find set X returns a pointer to the representative of the unique set containing X. Why I am saying unique? Because no other set will contain X because they are disjoint. Now, as I have told you initially, that any choice of data structure is going to directly affect the efficiency of any algorithm. So, that means the kind of analyzing the running times of this data structure in terms of the operations is important. So, here we will discuss this in brief. So, analyzing the running time of disjoint set data structures is going to take place in terms of two parameters. One is n, which is the number of make set operations, and m, the total number of make set union and find set operations. So, here we are analyzing the running time in terms of two parameters. One parameter is n, which is the number of make set operations, or we can say individually it is the number of elements, and m, which is the total number of make set union and find set operations. Now, since the sets are disjoint, each union operation is going to reduce the number of sets by 1. So, let us say we are taking the set S1 and S2, when they are joined there will be only one set. So, earlier there were 2, now it is 1. Now, let us say for example we are joining n number of elements. So, after n minus 1 union operations there is going to be only one set which remains. Since the sets are disjoint, each union operation is going to reduce the number of sets by 1 to be precise after n minus 1 union operations. Therefore, only one set is going to remain, and the number of union operations, thus it can be at most n minus 1, and also since the make set operation, which is denoted by the number n, are included in the total number of operations m, we have m greater than equals to n, that we have. Now, in order to understand this whole thing, let us take an example. So, here on the screen you can see that I have a forest, I can say, or I have 4 different components of a graph. So, one component is having A, B, C, D, another one is having E, F, G, and third one is H, I and J. Now, what has actually happened with these components? Let us try to see. So, initially they were the collection of disjoint sets starting from A to J. So, these were the initial sets, and by as we can see different edges, we will start processing the edges. So, the first edge which is going to be processed is BD. So, when we are going to process this BD, that means now B and D are going to make one set, and obviously one representative is going to be designated. So, now the sets we have A, B, D, C and all other starting from E to J. Now, next let us say we are processing E, G. So, E and G will be combined and obviously the result will be one set less than the previous step. So, here you can see E and G is now combined, and I am assuming that E is the kind of element, representative element for this set, and B is the representative element for the previous set of B, D. All other elements have themselves as the only member and as the representative as well. Now, AC when combined is going to give you an edge, the representative element assuming is A. Then we are performing H and J. So, H and J now you can see on the fifth line are going to be combined. Similarly, when A and B are combined, now this is something worth noticing, A and B are combined. So, B is the representative of the set BD, A is the representative of set AC, these are combined and the set will be A, B, C, D and the representative is A, that is why we have chosen the column A, this is what the convention we have adopted for. Then EF, so EG is one and F is another, so EF combined and EFG, and BC finally BC is already combined in one. So, it is not going to differ anything. So, this is what how these edges are being processed when we take the example of these connected components. So, earlier they were having a collection of disjoint sets. By combining them using the union operation, we have combined all the sets and the resultant sets are here. So, in this lecture we have seen the union find data structure which are for disjoint set operations, and we have seen what are the what is the application, what are the application areas where they can be used, and we have also seen the operations which can be performed on these union find data structures. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next lecture. Till then, take care. Goodbye.